Hey guys, welcome back to another video. Today we are talking about inequalities. So we are starting off with an introduction and we'll do some notes today. Right now, these are not part of your notes. I'll tell you when you can start copying down. But we're going to start off with a few examples and we're going to relate it back to the equations that we've been learning about. And the good news is about inequalities is they're very closely related to equations, and we can draw on a lot of that information we've learned. So we're going to start with a quick review and then get into your notes. So our first example says Brian needs to cook the sugar to 165 degrees Fahrenheit to make caramel. So when we're talking about this situation, we know that there's only one temperature Brian can cook this caramel to in order to get it exactly right. If he cooks it too hot, it won't be right. If he cooks it too cold, the temperature isn't right, it won't be right. So there's only one thing that will work for Brian. Brian has to get it to 165 degrees. So our number is exactly 165 degrees. With inequalities, we are talking about situations where lots of different situations would work. We don't have to have exactly the right number. So, for example, Jada needs to get a grade higher than an 85 on her next test in order to get an A on her final. So she has to get something bigger than an 85. Well, what would work for Jada to get an A? Well, she could get an 86. She could get an 87. She could get a 90. She could get a 92. She could get a 100. Any of those would work in order to get Jada what she needs to get an A. So we can represent that by saying our number has to be bigger than 85. And the way we do that is with an inequality symbol, and it looks like this. If you remember, way back when you learned about inequalities in the past, inequalities have the greater than or less than symbol, which looks like this is our greater than symbol. And then this is our less than symbol. And what this does is it compares two numbers. So it says whichever side, the bigger side of the inequality, this side, is facing, that number is larger. And we can kind of look at an example like 100 is bigger than 1, or 30 is bigger than 2. So we're just looking at greater than or less than, comparing numbers, making sure that the big side of the symbol, the greater than or less than symbol, is facing towards the larger number. So for example, if we had the number 1/2 and 15, we know that 15 is bigger, so the big side is facing the bigger number. And to reverse that, we could write the same inequality backwards, and now we're using the greater than symbol. This reads 1/2 is greater or less than 15, and this reads 15 is greater than 1/2. We're still comparing the same two numbers, but we're looking at it different ways. So in this example, Jada doesn't have to get exactly an 85. In fact, she can't get an 85. She has to get something higher than that, something higher than an 85. So she's got to get a number that's bigger than that, which means we need any test score or any score that is higher than 85. Another example is Jason has $20 and his mom says he is not allowed to spend all of his money. So when we want to know what can Jason spend, if we take our number, what can he spend? He could spend $10, he could spend $5, he could spend $0. He could spend $19.95, all the way up until $19.99. As long as he doesn't spend all $20, his mom is happy. So our number compared to $20 has to be smaller, which means the symbol is facing kind of away from the X. That means 20 has to be bigger than whatever Jason spends. So today we're going to quickly talk about just a few simple examples of inequalities, and we're going to talk about what some solutions could be. We're going to write the inequality and we're going to graph it. And then you're going to practice that later. So Abby spends fewer than 8 hours working out. So this is a situation where we don't know exactly what she spends. And in fact, we know that she doesn't spend exactly 8 hours, but we know it's smaller than that. So when we talk about some solutions, we could talk about Abby spending 0 hours working out. Abby could spend 2 hours working out, 1 hour working out. She could spend 7 hours working out. She could spend 7.5 hours working out, or even 7.999 hours working out. But all of these numbers, what do they have in common? All of our numbers, so this is our solution set. These are possible solutions. We're not including all of the solutions because it would take too long. In fact, it would take an infinite amount of time. We could just keep coming up with different numbers that are less than 8. But we know it has, whatever our solution is, it has to be smaller than 8. So we can write this like x is what? X is smaller than 8. So the small end needs to be pointing towards the x. Whatever x is, it has to be smaller than 8. We could rewrite this the other way, like that. But we wouldn't use the same symbol because now the x is bigger than 8, and that doesn't work. So we would have to flip the symbol over if we rewrote it the backwards way. So we need to make sure that x is the small one and 8 is the big one. So whatever our answer is, it's got to be smaller than 8. Now, when we want to graph that on the number line, it used to be we could just go and we could say, oh, okay, 8, and put a dot. However, we're talking about all the numbers that are smaller than 8. So any number that's smaller than 8. So what I could do is I could say that we could graph some of our solutions. Like we could say, all right, she can work 0 hours. She'll work out 0 hours. She could work out 2 hours. She could work out 4 hours or 6, or in between 1 hour. She could work out negative hours. I honestly don't know how you work out negative hours, but any of these solutions would work because the only condition is that it's fewer than 8 hours. So we could just keep on graphing, or we could show all of the numbers that are smaller than 8, which is the solutions that would work here. All of the numbers that are smaller than 8. So we could go in and graph all of these, and this is what we'll do is we'll kind of shade in all the numbers all the way up, and we need an arrow pointing to indicate that we're talking about to infinity. And this goes all the way up to 8 hours. Now, we're going to draw a dot where the 8 hours is, but we are not going to include 8 hours. So if we wanted to say that she could work out 8 hours, we would bubble this in. We would shade it in. But 8 will not work because 8 is not fewer than 8. And 8 is not a solution for our situation. If Abby spends 8 hours working out, then it doesn't fit in with our sentence. So that's how we graph this inequality. We draw a circle around where we start, but we don't shade it in like we did all these other numbers because we're not going to include 8. And you'll see a few more examples of what that looks like. So here's another example. Carlos wants to beat a high score of 20 on Brick Breaker. So he's playing a game. He wants to beat the high score of 20. So what are some scores that Carlos could get to break the high score, to beat the high score? So he could get a 21, right? He could get a 25. He could get a 26. 27. We could keep going. He could get a 30. He could get 100. He could get 200. He could get 1,000 points on Brick Breaker. Any of those scores will beat the high score. What won't beat the high score is a 20 or a 19 or an 18. None of these will work because he's not trying to tie it or get less. He's trying to beat the high score. So what we're going to do is we're going to go to 20. Oh, sorry. We need to write our inequality. So what numbers would work? Our numbers have to be, compared to 20, our numbers have to be bigger than 20. So we are going to draw the symbol facing, or the large side facing the X. And we can rewrite that, but we've got to flip the inequality symbol around, making sure that the X is big or bigger than the 20. I'm going to rewrite that. So either way, the X has to be bigger than 20. And the way we graph that is we go to 20 so that we know we start there. But we're going to include all the numbers that are bigger than 20, which means we're going to include like right up next to it 21, 22, 20.5, any of those. And then we shade it in. Your teacher may have a different opinion on that. You need to check with them. Some teachers prefer, and I'm going to back this up so you can see a different example of the way that would look. Some teachers prefer you just shade in like one line like that. However your teacher is asking you to do it that way. If your pencil is small, and for example, I'll show you what that looks like on a, like if you were to work on your paper. So if your paper looked like this and you drew a line, well, if you drew a line and then you just drew in with pencil, it might be a little difficult for us to tell which way you're pointing your arrow or which way you're shading in, especially if your pencil is like blending in with the ink on the paper. So that's why I'm kind of drawing a big line or shading in like that. Just clearly indicate which way you're talking about on the number line. And so because X is the bigger number, or X needs to be bigger, we are going to shade in all the numbers that are bigger than 20, and the bigger numbers are to the right on a number line. I'm going to go back down. Okay, so the new thing, or the thing that you may not remember from 6th grade, is the greater than or equal to sign. So for example, let's talk about Bobby. Bobby, he needs to make at least $10 today. So what are some numbers that Bobby could make? Bobby could make $15. He could make $30. He could make $100. He could make $11. He could make any amount of money. He could make $10.01. But he needs to make at least 10. So when we say we need at least 10, we are also including 10. 10 would also work here. So at least 10 means $10 and up. So when we write that, we are going to say X needs to be bigger than, just like we did earlier, but we're also going to draw this line equal to. And so the greater than or equal to symbol looks like this. This means that X can be any number that is bigger than or exactly 10. And we can rewrite that. But we just need to make sure we keep the X is bigger than or equal to. So this symbol is like if greater than and equal to got together and merged, and we used a line from the equal to sign and the greater than symbol, and it's a combination of the two. So how do we graph this? We're going to do exactly the same thing. We're going to go to where 10 is, okay, and we're going to include all of the numbers that are bigger than 10. So we're going to include all the numbers bigger. The numbers that are bigger are to the right. We're going to include all of those, but we're also going to include 10. So unlike these, we were not including 20. We were not including 8. So we did not bubble them in. We did not include them or shade them. But here, we want to include 10, So we're going to color that dot in so we know that one, where that one is included in our solution set, that number. So that's greater than or equal to. Let's talk about Sunny can spend at most 15. And at most is a little bit tricky. At most means up to $15 at the store. So if you're thinking about Sunny in this situation, Sunny can spend up to and including at most 15. The most they can spend is 15. So they can spend $15. They can spend $14. They can spend $14.01 or $14.99. But Sunny cannot spend $16 or $15.01. The most that Sunny can spend is 15 bucks. So when you start to think of your solution set, you're talking about 15, right? And can Sunny spend 15? Yeah, just that's the most he can spend, or she. And anything less than that. So we're going to include anything less than that. And the numbers less are to the left. So the smaller numbers are to the left. But we're also going to include 15. And I forgot to write my inequality again, so we'll do that now. We're going to also include 15, so we're going to bubble it in. And how we write that inequality is we say, okay, what do our numbers need to be? Do our numbers need to be smaller or bigger than 15? Our numbers need to be smaller, so we're going to put the small end facing the x, but we're also going to include 15 by drawing the line. And that can be rewritten this way, just making sure that the x is the small one and 15 is the large one. So that is a quick fire example of, or several examples of inequalities. We're now going to get into our notes, and they are going to get a little more complicated as we go. Before you get started, I need you to pause the video here, and I need you to write down this chart. Some of this chart will be repeated in the other notes, but you need to have this one as a kind of a quick reference back to. So I need you to label the top of the page inequalities and copy this chart down, and go ahead, pause the video, do that. I'm not going to take a pause. I'm going to move on. Okay. So we are going to talk about two-step inequalities because that is more geared towards 7th grade. We just did a quick review of some of the stuff you know from your past, and talk about inequalities and what they mean in real life. So you should have a copy of these notes in front of you. If you do not, pause the video again, get that copy in front of you, and I'm going to pick a color just for the sake of a new color. I think we're filling blue. All right, so identifying an inequality word problem. So you need to be thinking about, when you're reading word problems, how do you know it's an inequality word problem? And so let's look at how we can identify them and then write them. Write an inequality based on the word problem. So when given a word problem, it can be helpful to write an equation, and you are writing down with me, you are following along on your notes. To write an inequality in order to guide your process when solving the problem. Which word problem below is describing an equation and which is describing an inequality? Circle or highlight any words or phrases that might help determine the difference between the problem. Okay, so John has a vacation savings goal of at least $1,500. We're going to go ahead and highlight or circle depending on what you have in front of you. At least is a key word. At least to me means that we have a goal of $1,500, but John's not going to be upset if he saves more money than $1,500. At least means $1,500 or more. Okay, So he has already saved $350. He will mow lawns for $25 each. How many lawns will he need to mow to reach his savings goal? I'm going to zoom in so that I can write a little smaller. This is an inequality because we know that there's not just one number that would work here. John could make $1,600, he would be happy. $1,700, he would be happy. $2,000, he can make more than that. So we're just looking for any number that would get him $1,500 or more. All right. Now, John has $350 in a savings account. After saving $50 each week, he has $650 in his account. How many weeks of saving $50 did it take for John to save this amount? This is an equation. This means we're going to find an exact one answer. There's only one solution that would answer this truthfully, okay? And we'll go to writing an equality here in a minute. This is a little bit of a repeat for you, so I apologize about that. But it's good for you to have a couple of charts and a couple of examples of these words and phrases. So these are some common things you may see, at least, no less than. These mean that X is greater than or equal to whatever the number is. So that means if someone needs to make at least a certain amount of money, they can make more than that. That number can be bigger. Or no less than. If I can't make any less than $1,500, I could make more than $1,500, and that's okay. So a lot of the times these words are a little misleading. You're going to have to really think about them. Like when you hear less, you're going to want to think of the less than, but this is actually kind of the reverse. If I want to make no less than $1,500, then my number has to be bigger than $1,500. So these next few, same thing. At most, no more than. Those mean less than or equal to. So if I want to make at most or no more than something, I need to stay under that, which means I'm talking about numbers that are less than that. So X has to be smaller than or equal to that number, whatever that number is. And our last two, less than and greater than. And it is important to point out that these mean but not including. So remember that if we are not including the number, if I need to make more than something, I have to go over that. I can't have that exact amount. So let's move on to what we are going to do when we walk into a word problem like this. This is the problem from above. John has a vacation savings goal of at least $1,500. He has already saved $350, and he's gonna mow lawns for $25 each. How many lawns will he need to reach his savings goal? So the first step, we're gonna write down some steps to helping us write out an inequality problem. So the first thing you're going to do is identify the variable. Make sure you're writing down what I'm writing down into your notes. So first we need to define the variable. What is the missing value that we're attempting to solve for? So if we are asking ourselves, what do we not know? The answer to that is how many lawns. So how many lawns will he need to mow? We know he's going to mow lawns for $25 each, but we don't know how many he needs to mow in order to get to his savings goal. The second step is identify the total And this is going to be just like in an equation on that other side of the symbol. So instead of an equal sign, we're going to use an inequality symbol. But our total, which we know here is going to be $1,500, is how much that's our goal. That's what we're either trying to stay over or under, or exactly at. Okay, and decide how your other variables relate to your other values relate to your variable, as well as identifying the inequality symbol. And then solve the resulting inequality using inverse operations. Okay, so I'm going to go back through those steps a little bit as we write out our inequality. So we've already done the total. That part I feel like is the easiest usually. That was our goal. And the variable expression is we're going to come over here and identify what is going on with John. What has already happened for John? So we know John had $350 already, and we know he's mowing lawns at $25 each. Okay, so our variable is representing those lawns, and this person uses the L for their variable, and y'all know I don't like that because it can look like a 1. So what we're going to do is we're going to use the letter X. So we know it's 25 for each lawn, and we know however many lawns he mows, he's going to do 25 times that. So if he mows 5 lawns, he's going to do 25 times 5 to get how much money he earned for that. But we're also going to add in his $350 because whatever he gets from mowing the lawns, he's going to add that to the $350 he already has saved. And that's what we're comparing to $1,500. So what do we need from this? This is the money he's earning. Do we need this number to be smaller or bigger than $1,500? Do we need this area over here to be more money or less money than $1,500? We need it to be more money. So what we're going to do is we're going to have the inequality symbol, or the greater than symbol, facing the bigger side, facing this way, okay? Because we need this to be bigger than this, okay? So the next question is, do we include $1,500? Can John make exactly $1,500 and reach his goal? And the answer is yes. At least $1,500 means as long as he makes $1,500 or more, we're good to go. So we're going to include the line that indicates or equal to. And then the last thing we're going to do is we're going to solve it. 25x plus 350 is greater than or equal to 1,500. So as long as this is bigger than or equal to 1,500, we're good to go. So you can solve this just like I am. You can solve it along with me. I'm probably going to need to, I'm probably going to run out of room here. So what I'm going to do is include some more room in order for me to get this. You may need to put this on like a Post-it note or on your journal. But I'm going to draw a line and I'm going to solve just like I would. So what's happening with x? We are multiplying it by x and then we're adding. So we're going to undo those. Let's get rid of the 350. And we cancel out positive 350 with negative 350. I'm going to do that on the other side as well. Whatever I do on one side, I have to do on the other. This cancels out. This right here will, this won't cancel out, but it'll give me a different value. 10 minus 5 is 5. 4 minus 3 is 1. Now we have 1150. So once we take off the savings of 350 that he already had, now we know that he has to make $1,150 just mowing lawns. And lastly, we're going to get rid of this 25 by dividing. So multiplying by 25 and dividing by 25 cancel out. Got to do that over here as well. And this is where I needed more room. So We're kind of lucky here because we're working with 25s. And 25s are like quarters. So we know 25 won't go into 1 or 11, but it will go into 115. And so we can kind of count on our fingers 25, 50, 75, 100. And I know that 25, like quarters, 25, 50, 75, 100, that makes $1. So another 25 would make 125. I can go out and check that if I need to. Yeah, so times 5 is too much. So I know I'm going to make 4 here. That will give me remainder of 15. And once I bring down my 0, I can keep counting 25s. But I can also say, like, I'm pretty close here with this 125, so I can just go up 1. And I get 150 exactly. And I have a remainder of 0, so I can stop here. My answer is 46. X has to be, and I'm kind of out of room here, so just imagine that this isn't here, and I've got X. It's greater than or equal to 46. He must mow at least 46 lawns. So we know that he needs to mow 46 lawns or more. He could mow 47 or 48 or 50 or 100 lawns. As long as he mows 46, he's going to reach his goal. All right, so here is another example. Once we are done with these notes, you're going to go in and you're going to do some similar examples. And you'll have these notes to kind of back you up. So Will is attempting to decrease the number of calories he eats every day. His goal is to eat no more than 1,800 calories a day. He will always eat a 270-calorie smoothie for breakfast, plus 3 other meals. What is the average maximum number of calories he can eat for each of his other meals to meet his goal? So step 1, we need to identify our variable. So we're asking, what are we looking for here? What do we not know? What is our unknown? So usually our unknown is what they're asking us. What is the average maximum number of calories he can eat for each of his meals? And it's kind of the thing, how many calories can he eat each meal? And we know he's going to eat 3 meals, whatever these calories are. We're going to use C for calories. He's going to eat 3 of those meals a day, and at times however many calories they are, plus the 270 calories from his smoothie. And we know his total is 1,800. Now the question is, we're not writing an equation here because it says, sorry, get my pen back, no more than. And if you go back up to your notes, which mine has this paper in the way, no more than should be the less than symbol, less than or equal to. But let's check it. Let's see if it makes sense in our problem. We want our calories for the day. These are our calories for the day. Do we want those to be less or more than 1,800? We know it needs to be smaller than 1,800, so we're going to have the small side facing our calories for the day. Or he can eat exactly 1,800. So we're going to include the line underneath because it says no more than. That means it can't exceed that, but it could be exactly that. And then we're going to go in and we're going to solve. So we're going to draw our line. We're going to get rid of the 270 first. This will cancel out, and we're going to borrow 10 minus. I didn't need to do that. I apologize. 0 minus 0 is 0. We didn't need to borrow for that one. But 10 minus 7 is 3. 7 minus 2 is 5. And now we know that once we take the smoothie off, his 3 meals the calories from those 3 meals have to be under 1530. And once we get rid of the 3 by canceling it out, we're multiplying by 3, so we're going to divide by 3 to cancel out, and we got to do it on both sides. Now we need to go into 3 will go into 15 5 times. 3 times 5 is 15. Bring down our 3. 3 will go into 3 1 time. We'll get a 3, and we'll have a 0, and we'll bring down our 0. 3 will go into 0 0 times. I don't need to add a decimal or, I don't need to add a decimal or continue because there's nothing left to bring down. So we know that our answer C has to be smaller than or exactly 510 calories per meal. We could also rewrite this. So I'm going to go back and rewrite my inequality where we have the 1800 on this side. You won't see this as much, but know that you can rewrite it so that the calories that he eats all day have to be smaller than the 1800. So we need the small end facing that way. So we would just flip our inequality around. All right. And our last little bit is example 3. So what I'd like for you to do is to pause the video. Nobody's going to know if you don't do this, but I really would like for you to try. See if you can get this right on your own. So pause the video here. Try it on your own. It's multiple choice, so you've got, you know, something to choose from. And see if you can solve. I'll read it for you first, and then I'll let you pause it. On tax-free weekend, Hannah is shopping for clothes and can spend no more than $60. She finds a pair of jeans for $25 and is now deciding on how many shirts to buy at $12 each. Which inequality can be used to solve for how many shirts Hannah will be able to purchase without going over her budget? And then they're asking you how many shirts will she be able to buy without going over budget? And then they're asking you to kind of define her purchasing options. So Hannah will be able to only purchase 1 shirt, 1 or 2, 1, 2 or 3, 1, 2 or 3 or 4. So pause the video right here. See if you can get this on your own. I'll let you do that. All right, now I'm going to go in and solve. Hopefully you tried it. So on tax-free weekend, Hannah is shopping for clothes and can spend no more than $60. She finds a pair of jeans for $25 and is now deciding how many shirts to buy at $12 each. So defining our, I'm going to go a little bit smaller with my pen. Defining our situation here, our first step is to find the variable. So what is our variable? And we're talking about how many shirts. And we know that that's the thing that we don't know. That's the unknown quantity here. So we know they're $12 each. So it's we know it's going to be $12 times whatever the amount of shirts she buys. And you can kind of see that, like it's kind of multiple choice you into knowing that it's 12S. All right. And then we also know that it's going to be $25, and y'all can kind of see why I don't like the S as a variable there, because I've written it. It looks just like a, it just looks like a 5 in my opinion, but I'll make it a little curlier so to weed that out. And then we also know the jeans are $25. So this is the amount of money she's spending, right? This is her bill. And we want to know, or we want to make sure it is no more than $60. So our total is $60. And do we want the money she spends to be smaller or bigger than $60? We want it to be smaller, so it needs to be smaller than. And so that kind of eliminates C and D. And we we are seeing that it's no more than 60, which means it can't be bigger than 60, but it could be exactly 60. So we're going to include the equal sign, which means our answer is B, and I hope you picked B. All right, and now we want to go in and solve it. Okay, so we can draw our line. This makes sure we're doing the same thing on both sides. All right. And we are going to go in and we're going to subtract out the 25 to cancel that out. And if I do that over here, we know that she can, when we take the jean money off, we know that she can spend $25 on shirts. And so if they're $12 per shirts and we got to stay under that $25 or exactly that $25, we get rid of the 12 by dividing. And so now we have 25 divided by 12. So S has to be smaller than or equal to whatever 25 divided by 12 is. And we're going to go in. 12 can go in, it can't go into 2. It can go into 25 2 times. 12 times 2 is 24. And now we do have a remainder. So we're going to put in our decimal and we're going to bring that up into our answer and bring down our 0. 12 cannot go into 10. Oops. I messed up. Okay, so it happens. It does. I hope you. I don't know if anybody sees where I messed up, but we're gonna go back. I don't know if you can see. Here is where I messed up. 4. I crossed out the 6 and put a 4. I should have put a 5. So 5 minus 2, or 5, yeah, minus 2 is not 2. It is 3. So now we have $35 that we can spend on, sorry, canceled that out. We can have $35 we can spend on shirts at $12 a shirt. So now we need to see how many times 12 can go into 35. I apologize about that. So 12 can go into 35 how many times? 12 cannot go into 3. It can go into 35 still 2 times. 12 times 2 is 24. And that leaves us with a remainder of 11. And now we need to include our decimal. So we're going to bring down the 0. Now 12 can go into 110. That we don't know, or you might not know off the top of your head. So if you know your 12s, wonderful. If not, I know that it's close to 12 times 10 because 12 times 10 is 120. So I'm going to get close to that. I'm going to try 12 times 9. 9 plus 1 is 10, 108. Okay, 108 is very close to 110 without going over. So we're going to put a 9 here. 12 times 9 is 108. That leaves me with a 2. I'm going to bring down another 0. 12 will go into 20 one time. 12 times 1 is 12, and we have an 8. And 12 can go into 80. We don't know. Maybe you know your 12s. I know 12 times, let's try 6. That was wild. 12 times 6. 6 times 2 is 12. 6 times 1 is 6 plus 1 is 72. 12 times 7 is 84 is too much. So we're going to do 9.1. 12 times 6 is 72, and we have an 8 left over. Bring down the 0. 12 will go into 80. We already know that. 6 times 72. Hopefully you recognize what is happening. We have a repeating digit. So Hannah can buy, I'm going to get rid of, I don't know what happened over here, but let's divide by 12. And that gets rid of that. So S has to be smaller than or equal to 2.916 repeating shirts. 2.916 repeating. Now, If you go to the store, can you buy 2.916 repeating shirts? Absolutely not. So let's think about what that means in this situation. We can take our inequality, which is 12 times how many shirts plus the $25 jeans has to be smaller than or equal to 60. And we can go in and we can sub in. Now, what this means is S has to be smaller than or equal to 2.916 shirts, which basically means 2 shirts. So if you think about it, if she buys 2 shirts, that's $24, right? And 24 plus 25 is $49. Does 49 fall under the $60 limit? Absolutely. So she can buy 1 shirt for sure. We know that, right? Well, let's not bubble that in yet. So we know she can buy 1 shirt. She can also buy 2 shirts. So let's see if she can buy 3 shirts. So if they're $12 a piece, and 12 times 3, plus the $25 jeans, does that stay under the $60 budget? 12 times 3 is 36. And 36 plus the $25 jeans, 3, 4, 5, 6, is $61. Is 61 less than or equal to 60? No. So she can buy 1 shirt, she can buy 2 shirts. She cannot buy 3 shirts, or she'll be going over the budget. So Hannah can buy 1 or 2 shirts without going over budget. Certainly she can't buy 4 if she can't buy 3. All right, guys, so now you're going to practice. Make sure you take these notes, glue them into your journal, and we will see you next time.